And the thing is that we are not going to talk about the Kuramoto model anymore. I'm sorry. So I know you are familiar with it, but we abandoned completely the Kuramoto model. And we are going to focus on one very, very interesting and useful tool, which is the master stability function, okay? How many of you have heard, not used, but heard about the master stability function? Two, only two, three, four, five. Okay, five. Five is okay. One thing about the lecture of today is that it contains not very difficult mathematics, but contains a lot of index and calculations are a little bit cumbersome, okay? But don't worry. I mean, the important thing is that you follow me and that understand the final message, how to use it, okay? What is this and how to use it in a proper setup. Okay, so abandoning the Kuramoto model is because we are going to change our focus, okay? Up to now, we have studied the synchronization transition. Here you have the typical synchronization parameter, the Kuramoto parameter, for instance, and here you have the coupling. And we have studied the passage from the incoherent regime to the onset of synchronization. And we have focused on this quantity, which is the critical coupling between the dynamical units, the oscillators in the case of the Kuramoto model, that what's the expression and what's its, the influence of the architecture of the interactions between the units. And we derived yesterday how the expression of this threshold, this synchronization threshold in terms of the adjacency matrix, in particular of the maximum eigenvalue of the adjacency matrix. And also once we understood a little bit the characteristics of this transition, what we did is play with this transition, and we turned this typically smooth synchronization transition into an abrupt one, which we call explosive synchronization. Okay, now we are going to focus on this other part of the diagram, which is the full synchronization state. And the question is, if we have a system in a fully synchronized state, this synchronized state is stable, and if it is stable, until when it is stable, okay? The stability question is the focus here. Okay, this is a question which is really, really important for many systems, but especially for one, which is not the brain, okay? It's not the brain, it's not only the brain. And it's, for instance, this power grid, okay? If we have a power grid, we need that all these generators and all these transforming stations are synchronized in order to have a proper operation of the system. In fact, if there is a disruption, the problem is to turn again to have the network operative because of synchronizing all the nodes of the network. Tell me. Okay, thank you. So, no, it was not a question, it was my fault. So given a network, can be this or can be other, is the synchronized state stable or not? So the problem is very easy in principle, okay? Because we have a network with n nodes, and imagine that each node is a dynamical system, okay? And this dynamical system for each node contains m degrees of freedoms, m variables, okay? For the Kuramoto model was 1, m equal to 1, okay? For the Rosler system is 3, for the Lorentz system is 3, for the Sikevich neuron is 2, okay? It depends on the dimensionality of each dynamical system. So we have a total of m times m coupled variables, and if some function, some n times m dimensional function governs the dynamics of the system, then the stability of a fixed point, okay, which can be the synchronized solution, is given by the spectra of the Jacobian matrix, okay? Jacobian matrix is just a matrix, which is, in this case, this expression, which is the derivative of each component of the function f that governs the dynamics with respect of each variable, okay? Remember, we have this amount of variables, and we evaluate these derivatives in the solution, okay? So it's a matrix which is a number, a matrix of numbers, because are derivatives that are evaluated, okay? So they are numbers. Okay, the problem is that this is an m times m times n times m matrix. It's a very big matrix, okay? So the question here is if we can do something to disentangle the high dimensionality of the network, which is n, from the low dimensionality of the dynamical system, which is M, typically a low dimensional system. Can we do this? And the answer is yes, okay? The answer is the master stability function. So let's start from the very beginning. So we have a network, we have a node of a network, let's say node I. The node I is characterized, its dynamical state is characterized by M variables, xi1, xi2, xim, okay? And obviously, this node is not alone, okay? But the dynamics of this node alone is given by this equation, okay? Which is a m-dimensional function f. Okay. Obviously, it's not alone. For instance, it has a neighbor, j, and this j is also characterized dynamically with these m variables, nj1, nj2, and jm. And I and j interact, okay? J interact with I with some function g, and I interact with j with some function g, which is different in principle, the function from each direction. And obviously, I interacts with many other neighbors. This is only one neighbor, so it receives inputs from other nodes with other interactors. So the complete equation is the dynamics alone plus the coupling, given obviously, and we are already used, by the adjacency matrix of the network, and these interaction functions that can be in principle different, okay? The first assumption we have to do, okay, and otherwise we cannot apply the master stability function, but this is typical, I mean, it's a situation which is usual in many dynamical systems, is that all these functions and all these functions are identical, okay? Obviously, the variables are not identical, it depends on the node, but the functions are f and g, which are the interaction and the single dynamical system of each node are totally identical. Okay, so now we have this equation. The function f is Rm, Rm. The function g is R2m to Rm. Can be whatever. Can be a Rosler system, for instance. And now the thing is that we have a symmetric, we are starting with a symmetric fixed point, which means that the system is in a fixed point of the dynamics, and the value of this fixed point for each node is the same, okay? It's identical. This is also a situation which is common, for instance, in synchronization, okay? Because it's identical. Okay, and the thing is that we have to study the linear stability of this fixed point in the system, okay? So what we do is to make a very small perturbation, so that now the dynamical state of each node is the fixed point solution, which is identical for all nodes, plus a perturbation which depends on the node. The perturbation is different in principle. Remember that this is an m-dimensional vector, and this is an m-dimensional vector because each node is characterized by an m-dimensional variable, okay? Up to now, everything is okay? Okay. So this is the equation when I do the perturbation, okay? This is the xi dot is the dot of this and this, the derivative of this and this, and here I put in the arguments of the functions, the expressions of the solution perturbed. And what can I do with this? I have to do linear stability analysis, okay? I make a Taylor expansion, and I remain in first order of epsilon. I assume that epsilon is so small that all the terms with epsilon to the square are negligible, okay? If I do so, I can concentrate in the evolution of the alpha component of the perturbation of node I. Alpha can take values from 1 to m, okay? Remember, while I is the node can take values from 1 to n. If I do so, these perturbations have different contributions from the linearization. I'm not going to do the linearization, it's just to make the derivative, but it's very, very easy. The first contribution is the linearization of function f, which contains all the derivatives of all the variables of function f evaluated at the fixed point, okay? Second, that contains the derivative of function g, okay, of all the variables, the first variables, evaluated also at the fixed points. And finally, we have the derivatives around the second, remember that this is 2m, the second variable, so the function g, the interaction function, that's why here are u and here are this v, okay, as evaluated also in the fixed point, okay. This is just the expression of the linear perturbation, the evolution of the linear perturbation around a node I in the component alpha, okay. The first thing is that we can compress this expression. This is a sum, okay? This is a summation across the variables alpha, so we can express it as this. The Jacobian of the function f, remember this function, the component alpha beta, because it corresponds to different, to this beta, beta 1, beta 2, beta m, from 1 to m, for all the perturbations or the rest of components of the node I. In the second case, we can put the summation as well. Here we have all the sums around these terms of the sum doesn't depend on j, so we can put it as k sub I, the number of neighbors of node I, and the sum of in beta of the Jacobian of function j. Okay? And finally, here we have a dependence with j, because here we cannot do the summation. Here we have not j, so we did the summation and the result is k sub I. Here we cannot do this, and we have to remain with the summation in j, and in a compact form, this expression reads this way. Okay. So we can put them together, and we have the three contributions. Again, the Jacobian of the function f of the single node, the Jacobian of the function j, the interaction, around the perturbation around the first variable, and the Jacobian of the function j, the interaction again, around or with respect to the perturbations in the second variable, the variable of the neighbors. Okay. This is a useless expression. I mean, this is right, but it's very, very, very complicated, right? Okay, let's focus on this. What I'm going to do now is to incorporate to these terms a sum in j in order to have it in a compact form. And to this end, we have put this delta j. Okay, this is the typical trick. So now we have all the terms in a double summation. J, that goes from 1 to n, and beta, that goes from 1 to m. Still, the two dimensionalities, n and m, are together in the same expression. So we are not satisfied. Okay, let's continue. What we do now is to express it, if you want, as a matrix of for index, someone say a tensor, and this matrix M is a n times m times n times m matrix, okay? This is the true Jacobian of the system, nothing more, nothing less. So we have to inspect the form inside this matrix. This is a huge matrix, okay? Imagine that we have a network of 10,000 Rosler oscillators. Then this is a matrix which is 30,000 times 30,000 matrix, okay? It's a huge matrix, okay? But it has some structure inside. I mean, we can explain. For instance, we can put the boxes. And now what we can do, you have 1 to n square boxes and 1 to n square boxes, okay? And each of these boxes can be labeled by the index of the node, ij1, i1, j2. So this is the influence of node 1 with respect to itself. This is the influence of node 1 with respect to node 2, etc., 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 okay? So these are boxes that are submatrices, okay? We have a total number of n times n submatrices of dimension m times n. In fact, if we check this matrix, we can say that all the matrices that are in the diagonal, because of this delta j, are of this form, okay? And we can color in green, in yellow. Then, what we have is that for each yellow, as I said, is an m times m matrix, okay? 1, 1, m1. Sorry, this is 1m. This is m1, 1m, sorry, mm. Okay, this is m times n matrix, and each of these matrices are also m times m. The thing is that all the matrices in yellow has this expression, okay? Because it contains this delta j that corresponds to the elements in the diagonal. Okay. So the thing is that these submatrices, which are low-dimensional matrices, so in the case of the Rosler oscillator, these are 3 times 3 matrices, okay, 3 times 3, contains the information about the evolution, okay, of the Rosler oscillator. Only depends on the characteristics of the first variable. And for the other boxes, what we say is that they are evaluated as this matrix dictates. And this matrix, as you remember, is the adjacency matrix, right? So this means that not all these blue boxes exist. only those that correspond to the neighbors of I exist. The neighbors in the nodes, pairs of nodes that are neighbors in the network exist. Okay, in this case, Aij dictates that there are these boxes, and in this case, this is a 0, this is a 0, this is a 0, empty, 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 because I and j in these cases are not neighbors. So here there is a 0. No, they cannot influence each other, so there is a 0. Okay, so this huge matrix has this structure. Okay, so one can say that we can put this as a tensorial product, okay, in which we have the identity matrix, which will be these diagonal terms, times a common box, a common matrix, which is the yellow one, okay, this is this expression, I have this, and the summation of the adjacency matrix, that is this blue colored coded matrix, and the tensorial tensor of a matrix which is identical. This matrix is identical to this, to this, to this, to this, and this Jacobian, okay? And if I do this, I can start do mathematics. Do you think it is correct? I can do this? No. No. I cheat you. Because to do this, we have to have that this matrix in blue are identical, and they are identical. And this matrix in yellow should be also identical. And it seems they are identical, but the problem is that we have this k sub I. So here k will be k1, here will be k2, here will be k3, blah, 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 to kn. So they are not the same. We cannot decompose it as a tensorial product. Still, we will do, but now no. So for the general case of a fixed point, which is symmetric, which makes that this matrix and this matrix and this matrix is the same, I cannot write the linear stability matrix, which is huge, as the tensorial product of big matrices I and A and small matrices yellow and blue. Okay? It's impossible. What can we do? Okay, we have to, if we cannot, we have to just evaluate the eigenvalues of M, which are M times N eigenvalues, and check if all these eigenvalues have real part negative. If all the eigenvalues have a real part negative, then I can say that this fixed point is stable. Otherwise, it's unstable. But again, this is not what I want. What I want to do is something easier, okay? So let's go to some special cases. The special cases come from the form of this interaction function, okay? Depending on the form of the interaction function, I can go ahead and make some simplifications. The first is that this interaction function does not depend on the state of the node, depends only on the state of the neighbor, okay? So I can write this as this, okay? J does not depend on the state of I, depend only on the state of the neighbor. This is a reactive interaction. It's very common, okay? For instance, in the Sikevich model, this coupling is reactive, okay? And in this case, if we have this, obviously, all the derivatives of this interaction term with respect to the first variable, because the first variable does not enter in the form, are canceled. And because the problem was located here because of this, and this is totally, and this is 0, then now, yes, I can write this as a proper tensorial product, okay? But only in this case if we have this interaction function. I repeat, it's very common, very usual to find this case. Okay, so now we have this special case in which we have removed the second term we have here. We have only 2 terms, and we can go ahead. Now imagine that we have the adjacency matrix, and we know a orthonormal basis of eigenvectors of this adjacency matrix. And obviously, this adjacency matrix have n eigenvectors, and with eigenvalues lambda nu. Okay, this is the expression of one of the eigenvector and the expression of the corresponding eigenvalue. Okay, if this is this, what we can do is to check the alpha component of each node, okay? So if I have, this is the, for instance, imagine that we have this, This is for the first node. This is for the second node. And this is for the, nth node, okay? So this corresponds to I equal to 1, I equal to 2, etc. And we have here alpha components, one each for one dimension, okay? So 1 to m, 1 to m, 1 to m, okay? And take, for instance, I take the second one here, the second one here, and the second one in all the components. And I construct a new vector corresponding to alpha equal to 2, because I choose the second component, and I have 1 to n, one per each node, an n-dimensional vector. Okay? This is okay. I can do it. Okay? If this is an n-dimensional vector, I can express this vector as a function of the eigenvectors of A, okay? And these are the linear coefficients of this linear combination. Okay, if I have this expression, the time derivative of this is just the derivative of the coefficients, because obviously the components of the eigenvectors do not change in time, okay? These are my basis, my new basis. Okay, so what I do is to take this expression and take this expression and substitute here and substitute here, okay? So here I have this one, I put here, and this one is here, I change it. Okay, here I put j because it was with j, nothing more, nothing less, okay? Now let me express this with the summation, with the 3 summation in a row, and do the magic. Now the first magic moment arrives, because I'm going to quit this summation. I will make this summation in J, and the only J's you have here is this one, which is in the delta, this one, which are in the adjacency matrix, and this one, which are in the eigenvector components, okay? This is an eigenvector of A, so when I make the product, I have the eigenvalue, and obviously this is an eigenvalue, an eigenvector also of the identity matrix, because any vector is an eigenvalue of the identity matrix. So I have this, and now I have no summation in J, and I have changed this by this. Nothing more, nothing less. Okay. Now, because it's an orthonormal basis, I can take each of the components in beta, okay? So each of the components in nu, each of the components of the eigenvectors, and solve it separately. And now I consider all the terms in alpha. Here I used alpha 2, but obviously you have to use alpha 1, the same rational we have performed, and alpha m, the same rational we have performed, okay? And if we mix it, we have this expression. And this expression, ladies and gentlemen, is an m-dimensional linear system. M, 3. We have passed from solving a linear problem of nm times nm matrix, and now what we have here is a m times m matrix. And they say something, hey, Jesus, yes, but they are n. Okay, but these are very simple to solve. And now the second idea, this is the thing, is the second brilliant idea, which was due by Pecor and Carroll, okay? They say, okay, you don't need to solve an n independent m-dimensional linear system. Consider one single linear system of dimension m, taking this not as the eigenvalue of the adjacency matrix, but as a parameter, as a free parameter, okay? In your model, you have parameters. In the ICTP-SAIFR model, we have A, B, a lot, P, C. So another parameter, lambda, okay? So we consider lambda as another parameter of the model. The other parameters appear here and appear here, okay? Okay, and now calculate the maximum eigenvalue of this m times m matrix as a function of lambda, and this is what is called the master stability function, okay? In this case, for the fixed point. So what we have is just a function. For each value of lambda, okay, I have a maximum eigenvalue, and I plot the the value of this maximum eigenvalue as a function of lambda. Okay? The important thing, and I know that most of you have not followed the derivation because, I mean, you have to do it by yourself the first time, okay? But the most important thing is this curve is only due to f and j, m-dimensional functions, okay, here. So are only related to the characteristics of the dynamical systems at work. Nothing to do with the topology, nothing, okay? So if someone say, okay, we have a collection of Rosler oscillators, and they are coupled with this function, okay, and the network, no, don't tell me about the network. I don't care. By now, I don't care. Just tell me the function, the dynamical system, and the way they interact. I compute the Jacobians, and I can plot this function according to this expression, okay? And where is the network? Well, the network is because we have here a parameter, but remember that this parameter should be an eigenvalue of the network, okay? So I take the network, I consider the adjacency matrix A, and compute the spectra. And the spectra goes from lambda mean to lambda max. And now, just check it. If all the eigenvalues here correspond to negative values of the function, then the system is stable. And we have light, okay? If you have a matrix, a connectivity matrix, in which you have, for instance, this spectra and some eigenvalues like this one and this one correspond to the positive values of the master stability function, then you have it unstable and we have no light. But the important thing is that we have achieved the goal. We have completely decoupled the n-dimensional thing, the network, from the m-dimensional thing, which is the dynamics, okay, which are totally different in the order of magnitude. Okay, I have time. So the thing now is that we have done it for that when this case was at work. Remember, this is only valid if we have a reactive interaction. In the sense that the interaction with the neighbors only depends on the state of the neighbors, not on the state of the node, okay? And this is something very usual. Another assumption can be this. The function g, okay, remember that in general, the function g depends on xi and xj, takes the special form of xi minus xj, okay? It's a particular form. This is called diffusive interaction. Diffusive interactions, okay? Depends on this. And if we do have this, remember that we have a problem. We cannot split as a tensorial product because of a third term. Now this third term appears again. But the thing is that this term that was very problematic, in the case of this coupling, can be also removed. I mean, the problem that makes this term is removed by considering this kind of coupling. Why? Because if I have this kind of coupling, the Jacobian with respect to the first variable of the interaction term is just minus the Jacobian of the interaction term with respect to the second variable, and we can call it dg, okay? And if I put this dg here, we have this. I say, okay, but you still have this. Okay, but now I'm going to introduce another matrix, which is very important in network dynamics. And I think it's the first time it appears in this course. And I'm sorry, in name of all the professors, which is the Laplacian matrix. Have you heard about the Laplacian matrix of a network? How many of you? Only 3. And Homer Simpson, which is not here today, but also knows. Okay, now look at this, and we can consider, we can incorporate this part into the blue parts. And we have this new matrix, okay, which is called the Laplacian. The Laplacian is very simple. It's just, the Laplacian is a diagonal matrix that contains the connectivities of all the nodes, and these are zeros, okay? This is a diagonal matrix, minus the adjacency matrix, okay? Is the analog of the Laplacian operator when you have a two-dimensional system, for instance, in which you have the derivative of a diffusion problem, okay, or in 3 dimensions. If you go to a network, this is the analog operator, and it's called Laplacian, okay? And it only depends on the topology, okay? Because it has the adjacency matrix and just the connectivities. Nothing more, nothing less. It only has to do with the connectivity patterns that you have in the network. You can use this matrix, or you can use the adjacency matrix. I mean, and they both have the same information about the structure of interactions. Now we are interested in using this matrix because it naturally appears here. And this is the Laplacian matrix. Let me put it this way, okay? And now again, I can do the same thing. I have the tensorial product, but now here we have the Laplacian matrix, okay? Nothing more, nothing less. Okay, this is df, only df, and this is dg. Remember, which dg corresponds both to the derivative with respect to the first variable and the derivative with respect to the second variable. And the story is the same. We can decompose in terms of eigenvectors of the Laplacian matrix, not the adjacency matrix. We can take each component in terms of these eigenvalues of the Laplacian matrix, and finally, you would derive a similar expression for the master stability function. The thing is that we will construct, you will compute the maximum eigenvalue of this matrix as a function of lambda, that is a parameter, and then you will evaluate with each eigenvalue of the Laplacian matrix, not the adjacency matrix. You have to do the same. So, if you have a system in which the interaction is reactive, so it's governed by the adjacency matrix, this lambda should be the eigenvalues of the adjacency matrix. If you have an interaction which is diffusive, like this one, then the strategy is exactly the same, the function is exactly the same, but these values should be the eigenvalues of the Laplacian. Nothing more, nothing less. Okay, and these are, you can have, again, the same. If all the eigenvalues of the Laplacians correspond to negative values, it's stable. Okay, and otherwise it's unstable. Again, we have decoupled completely the high dimension of n with the low dimension of the dynamics m. Okay, let's continue by considering the next step, which is not a fixed point, but a synchronized state. And the situation is the same. We are not going to repeat the steps because are the same. I will just mention the differences. The thing is that now we don't have a number, we have a solution. But the thing is that this solution, which is the synchronized manifold, is exactly the same to all the variables, okay? Again, we have a symmetric solution. In the first case, the symmetric solution was a symmetric fixed point. Now it's a symmetric trajectory because it's a synchronized state, okay? Okay. Then you do exactly the same, and you construct this function. The thing is that now you don't have to compute the largest eigenvalue, but you have to compute the maximum Lyapunov exponent, of this linear system, okay? And that's all. Again, these lambda values should be evaluated with the adjacency matrix if we have a reactive interaction, or Laplacian matrix if we have a diffusive interaction like we have here, okay? Exactly the same. Let's put some examples. Let's consider a Lorentz oscillator, okay? We are not going to make the mathematics, just to check what happened. We have this kind, we have a diffusive interaction, and in particular, we are we are considering that the interaction takes place only in the first variable. Remember that the Lorentz systems, M is equal to 3. It's a three-dimensional dynamical system. And the interactions between neighbors is diffusive and takes place only in the first variable. Okay, if you have this is the master stability function. Solution, your network. Here there is no network, okay? You have only the interaction and you have only the dynamical system. Without the network, I know that the eigenvalues of the Laplacian from the second to the largest should stay in this area. Otherwise, the system is not stable. Second variable, diffusive coupling, but now takes place in the second variable. Then you have this master stability function, so eigenvalues should be placed like this. And the funniest case is when the coupling between neighbors is diffusive and takes place in the third variable. In this case, you have this. Can be very funny, okay? So eigenvalues should be placed only in this part and in this part, okay? You have like two regions, okay? If eigenvalues are placed in these regions, then you have a stable state. Okay, let's go to the Rosler oscillators. Rosler oscillators, and now we are going to consider the coupling in the first variable, also a coupling which is diffusive, okay, is this way. In this case, J is 1, okay? This is JXY and JXJ. J is 1 because it's only XI and XJ. It's totally diffusive and it's controlled by this interaction coupling, which is important, okay? Then we assume that the coupling is in the first variable, and what we have is the master stability function. We can compute it by computing the Jacobian of the Rosler system and the Jacobian of this expression, which is really simple, which is 1. And we have this master stability function. And this is compute, you see these red dots, okay, it seems like a curve, but there are dots, is the spectra of an Erdos-Renyi graph. And in this case, you see that the Erdos-Renyi graph is not completely stable because we have something here which is in the positive part, okay? What happens if the coupling is the network of interaction is the same? The system is exactly the same, but the network of interaction is changed, and we change from an Erdos-Renyi network to a scale-free graph, okay? But we have this situation, okay? But again, we have that there is something here in the positive part. What we can do, okay, what we can do is to notice that this lambda is actually one eigenvalue times k. So I can increase k, and if I do so, what I can do is to control and insert the second maximum eigenvalue of the Laplacian, which is the minimum one, and put it in the correct region, and control the k, because if I increase a lot the value of k, I can lose the synchronization, I can lose the stability of synchronization because this maximum eigenvalue can cross to this border, okay? So with k, controlling the interaction term, what I have to do is to adjust in order that all the eigenvalues are in the region in which the master stability function is in the negative region, okay? Any question about the philosophy of the system? Because mathematically, obviously, there is some complications, okay? Yes? Mm-hmm. This is the Lyapunov exponent, okay? The master stability function can be computed from the maximum eigenvalue if you have a fixed point, or the maximum Lyapunov exponent if you have a solution, because you have to follow the trajectory. But this only affect this curve, okay? These are always eigenvalues of the interaction system. One is the dynamics, exponents, Lyapunov exponents, or maximum eigenvalues, and the other are maximum eigenvalues of the network, okay? Yes? Okay. So let's move, and we will finish, so Osvaldo can start before, with an application to neurons. And I tell Jordi, please, 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 explain the Izikevich model today. So he has to do it. Izikevich model, I remember, is a neuronal model which is not as sophisticated as the Hodgkin and Huxley model. It's a phenomenological model, in fact. And it was proposed by Izikevich because its simplicity and because it's very flexible. I mean, it allows a rich variety of solutions that corresponds to patterns observed in neurons. And as Jordi said, it's an ideal dynamical system if you want to explore what is the importance of the architecture of an interaction network on your neuronal dynamics. Because when you are interested in the importance of a network, because of the network is large, you don't care a lot about the single details of the neurons, okay? And now the question in this class is this. What is the influence of the architecture of a network, the eigenvalues of the Laplacian or the eigenvalues of the adjacency matrix, in the stability of the synchronization, okay? So this is the Izikevich dynamics, okay? This is when the activity of the node, remember, it's a two-dimensional system, x and y, and when the activity in the first variable is less than p, it corresponds to this equation. When it surpasses a threshold, then the variables are reset to a value in order to start again, and you can see this, okay? This is the typical dynamics. Here, in this case, you see that p, the threshold value is around 6, and the value c, the resetting for the x, is around -3, okay? So every time it reaches 6, it is resetted until -3. And this is more or less one typical dynamics of spiky dynamics of Izikevich model. What we are interested here is to apply the master stability function for fixed points, okay? We are going to do it for fixed points because we are interested in a problem which is I have a culture, have neurons, and they remain silent, okay? They remain like in a fixed point which correspond to the silent state, okay? And I can start adding some links, and the thing is when the architecture of interaction is strong enough, in order to trigger activity. And this activity, in terms of the fixed points, means that the fixed point solution has become unstable because of these interactions, okay? Not because of the dynamics. The dynamics itself is in a fixed point which is silent, but you start to put inputs in the network so that the fixed point of each dynamical unit is unstable and activity, the burst activity, starts in your culture, okay? So to this end, what we need is to attend to the interaction term. The interaction term typically in this model is a Heaviside function, okay, which is this with some threshold x super t. This is t. So this is the typical input that a neuron receives from the activity of a neighbor. This is the activity of a neighbor, a given neighbor. This is the threshold number, and the input is 0 until the activity of the neighbor is larger than this value, and then it corresponds to 1. Okay, this is the typical Heaviside. Okay, the problem to manipulate this kind of equations and to do operations is that this is non-analytic. I mean, there's a discontinuity. And one shortcut to do analytics here is to change a little bit the model so that this Heaviside function is replaced by this smooth function, which is just a logistic function, okay? The logistic function, if you have large enough gamma, corresponds very well to a Heaviside. Obviously, it's not a Heaviside, okay, because you have inputs here when you don't have to have, and it's not large enough here because it's not 1, but okay, it seems so, okay? So we change this interaction term by this expression. Okay, so the important thing from the master stability function is that we want the fixed point of the dynamics of the neuron, and this is the interaction terms. The interaction term is this hyperbolic tangent, but the important thing is that it only depends on the state of the neighbor, okay? The interaction between I and j does not depend on the state of I. So I'm in the situation in which this interaction function is of the first type. So I will be interested in the future in the eigenvalues of which matrix? Everybody, adjacency matrix. Okay? Okay, that's all. That's all what I need. Now, what I do is to take the Sikevich model, take the interaction, and just make the Jacobian. The Jacobian is 2 by 2 matrix. Wow, a 2 by 2 matrix. A 2 by 2 matrix can be analytically solved, the eigenvalues, okay? It's so easy that you can analytically write the eigenvalues. This is, remember that we have a culture of neurons, okay? 2 by 2. Okay, obviously, this should be related to the eigenvalues, this lambda of the adjacency matrix. Now, here you see this x star is the exact expression of the fixed point of the Sikevich neuron alone, okay? The Sikevich neuron alone contains these two null lines, and you have two fixed points, one stable and the other unstable. I don't write the exact expression of x star, but you can derive it analytically, it's very easy. And if you consider the expression of x and y of the fixed point, which is stable without any interaction, and you can explore these two matrices and explore which is the maximum eigenvalue, well, actually the two eigenvalues, okay, the maximum and the minimum, as a function of nu. And you have this. This is the master stability function. Well, actually, the master stability function is the blue one. This, and this, because you are interested always in the maximum. But I plot both because, okay, it's for the same price, I plot both. And the important point here, which is the important point here in this plot? Let's see if you have understood something. Which is the important point here? Not you, because I know that you know the master stability function. Which is the important point? So the important point is this one, okay? Before this point, the culture will be silent. After this point, for larger values of nu, the culture will have activity. I don't care about activity. What I care is that we don't have a silent culture, okay? And obviously, you can put the expression, you can calculate the value of nu at which these two eigenvalues are equal to 0, and you obtain this expression, okay? Remember that this is nu, and this is lambda, which is the eigenvalue, the maximum eigenvalue of the adjacency matrix, times the interaction term. So I put it here, and I'm interested in this value, okay? Given a network, which is the maximum interaction I have to put between networks in order to have activity. Or the other way around. Imagine that G is constant, and I'm interested in which is the maximum eigenvalue of the interactions that I need in order to have activity, which is what happens in reality, because the neurons start to make links. And as soon as they start to make links, they increase this maximum eigenvalue, okay? And, okay, just put along GC, and you have this expression. What I have done here is to put that the maximum eigenvalue of A, the maximum eigenvalue of this matrix, remember that is the second moment of the degree distribution divided by the first moment, okay? With this, what we saw yesterday, okay? I put it here. The maximum eigenvalue of A is equal to the second moment divided by the first moment, okay? And then we go to simulations, okay? We still don't have experiments, so hopefully we will have. And what we have is just to consider networks in which we change the average connectivity and numerically observe by increasing the value of G when these networks start to be active, start to trigger the activity, okay? And you see that the theory, which are the curves corresponding to this expression and the dots, are pretty similar, okay? So it seems that despite the simplicity of this function, 2 by 2 matrix, remember, you can do things that correspond to cultures that can be of thousands and thousands of neurons, okay? Obviously, remember, provided that you have some assumptions fulfilled, the interaction should be either reactive, and then you have to put the eigenvalues of the adjacency matrix, or the interaction is diffusive. In this case, you have to put the Laplacian spectra, okay? And I wanted to put this example because this was, well, it's not all the paper, okay? But this is a paper that we published, Jordi and myself, last Saturday. So all the calculations and going beyond to activity, okay, to real or biologically inspired networks with spatial correlations. That I know Jordi is fan of spatial correlations. You can download them. It's open access, so you can see all the detailed calculations on how to use the master stability function and also to use more refined networks. Okay, so. Yes, I think I'm done, so Osvaldo can start after me. Thank
you. One or two questions?
So you said that we were only looking for the structure of the network, right? So we didn't care about only the node, the local node.
Mm-hmm.
So
the local nodes and the interaction term. How the functional form of each interaction term. Yeah.
So where did you put this limit from? Like from this scale, I don't care, and this scale, I care. Where did you separate this?
What I say is you pass from a linear stability analysis, okay, which is the big matrix M, which is dimension mn times mn, and after some considerations, you end up with a matrix which is m times m, and that's all. So it's a big reduction. So you remove this dimension from the problem of the linear stability. So you have to check the linear stability now in a dimension m times n. The only thing